The second concept that we formalize in this lecture about matrices is the so-called inverse matrix, which is particularly important since in most applications, in real-world applications, we actually have to compute such an inverse. And it is actually computationally very challenging. So it is very important to formalize the idea of an inverse and to discuss some of the properties of inverses. So let's just start with a little bit of intuition of what the inverse is from considering a very simple multiplication. So consider that I multiply the number 3 with another number, and I want the product to be equal to 1, which is the sort of neutral numbers of multiplications. So the inverse of the number 3 is the number such that if I multiply 3 by that number, I obtain 1. And it is, it is easy to derive that that number is 1 over 3. So if I multiply 3 by 1 over 3, I get 1. Now, basically, we want something similar for matrices. So if I have a matrix A, I want to find a matrix that I'm gonna call A to the minus 1, such that if I multiply these two matrices, I obtain, well, sort of the null element of matrices, which is the identity matrix. Okay, so remember that the identity matrix is the matrix where I have 1 on the diagonal and 0 outside of the diagonal. So we notice that multiplication is not commutative. If I have two matrices A and B, A times B is different from B times A. However, if I have a matrix A and I compute its inverse, then it doesn't matter on which side I do the multiplication. So of course, since this is true, the inverse only exists for a square matrix. And if the inverse exists, we say that the matrix is invertible. So here we have the formula that if I multiply a matrix A times its inverse, it doesn't matter on which side, I get the identity matrix. First of all, the matrix A has to be squared, but even square matrices, all square matrices, do not have an inverse. There are some matrices for which the inverse doesn't exist. So it is very important to know when that matrix exists, and it turns out that it's the determinant of the matrix that tells us whether such an inverse exists or not. And in particular, the inverse exists if and only if the determinant of the matrix is not 0. If that inverse exists, it is unique. So each matrix, if it has an inverse, it's unique. It's only one, and a matrix has an inverse if and only if the determinant is not 0. So here we have one particularly important reason as to why we have to compute the determinant, because we have to check if a matrix is invertible, and we can do that by computing the determinant. Okay? So we spent a lot of time in the previous video discussing how we can compute determinants, and this is because it is particularly important to do because it allows us to check whether an inverse exists. So, well, here then there is a little exercise that it's also available in the tutorial, and I want to just very briefly discuss one property of the inverse, which is the second one here. So if I have two invertible matrices, A and B, then the product is an invertible matrix. And in particular, it is equal to the product of the inverses. So the inverse of a product is the product of the inverses. But notice that you actually have to reverse the order in which the two matrices appear. So the inverse of A times B is equal to the inverse of B times the inverse of A. So this may be a little bit counterintuitive, but this is the rule that one can prove it's true. Then the second important thing that I want to discuss is that, well, as we showed in the previous class, computing the determinant of a 2 by 2 matrix is very easy. And also computing the inverse of a 2 by 2 matrix is easy. So if you remember the formula of the determinant, we can find it here in the denominator. So we see that the inverse of a matrix is 1 over its determinant times some rearrangement of the entries of that 2 by 2 matrix. So the A here has switch position with the D. The B and the C are in the same position, but they now have a negative sign. So in exercises, I might ask you to compute the inverse of a 2 by 2 matrix. So this is something that you should be able to compute. Whilst I give you here also the rule to compute the inverse of any matrix. Now this is particularly challenging to do even for a 3 by 3 matrix. So in general, I will never ask you to tell me what the inverse of a 3 by 3 or a bigger matrix is. Whilst for the determinants, we saw exercises that where I ask you to compute the determinant of a 3 by 3 or a 4 by 4 matrix, where we took advantage of the expansion and some of the properties of the determinant. For the inverse, I may only ask you to compute the inverse of a 2 by 2 matrix, not of a bigger one, but as a reference, I give you the formula here where you can compute the inverse of a larger matrix.